Hey everyone, and welcome to this explainer on practical Rust, brought to you by Forge College. So, last time, we dug deep into Rust's absolute core promise, total memory safety, all thanks to ownership. Now we're going to build on that and take the next big step toward writing programs that are truly bulletproof.
Okay, so you've got a handle on ownership. Awesome. Your code isn't going to have those pesky dangling pointers or double freeze. But what happens when the real world decides to crash the party? What happens when the file you need to read just isn't there? Or a user types potato when your program is screaming for a number? That's a whole different kind of problem, isn't it?
And that's exactly what we're going to tackle first. We've used ownership to build this incredibly solid, memory-safe foundation. But now we have to build the rest of the house, and this house needs to be able to withstand the storms of, failed operations and totally unpredictable inputs. Now, this is where things get really interesting. In Rust, error handling isn't just some feature they bolted on at the end. Oh no, it's woven directly into the fabric of the ownership system itself. When something goes wrong, you can't just return a null pointer and, hope for the best. The compiler actually forces you to deal with the failure in a way that respects ownership, making absolutely sure you never pass around broken or invalid data. So how do we handle these potential failures? Well, welcome to your error handling toolkit. For this little coder's quest we're on, you get two incredibly powerful tools, option and result. And trust me, knowing which one to grab and when is the whole game. Let's break them down real quick. Think of option as dealing with absence. It's like asking, hey, is there a value here or not? It's a simple yes or no. You either have some value or you have none. Result, on the other hand, is for things that can actually fail. It's not just about absence. It either worked and you get an okay with your value, or it blew up and you get an error that tells you exactly what went wrong. And this table just lays it all out perfectly. You use option when a value not being there is, well, an option. It's expected. No big deal. You use result when a failure is a real problem and the part of the code that called your function needs to know why it failed. But look at that third column, ownership pattern. This is the key. In both cases, you return an owned value. You're not just lending the data. You are cleanly transferring ownership of the successful result or the error to the caller. No messy borrowing, no lifetime chaos. It's beautiful. All right, that's enough theory. It's time to see this stuff in action. Let's get our hands dirty and go on a little coding adventure to make all this feel a bit more real. So here's our mission. It sounds simple, but it is loaded with potential traps. We're going to read numbers from a file, turn that text into actual integers, and then add them all together. Every single one of those steps can fail, which makes it the absolute perfect training ground for our new tools. Now, before we write the functions, let me show you a really powerful pattern that all the pros use. Custom error enums. Instead of just throwing around generic error messages, we can actually define our own specific types of errors. This lets us be super explicit about what could go wrong in our program. Things like, the file was empty, or that wasn't a number. And here's what that looks like in code. We've made our own error type, parse error. It can be one of two things. Empty line, which is pretty self-explanatory, or it can be an int error, which actually wraps the standard library's own parse int error. And see what we did there? We're not borrowing the standard error, we are taking full ownership of it and putting it inside our own custom type. This is a classic ownership-friendly pattern in Rust. Now, if you were to handle this manually, you'd probably end up with something like this. A big, clunky match statement for every single operation that might fail. I mean, it works, but it's super verbose and it just clutters up the main logic of your function. There's gotta be a better way, right? Oh, you better believe there is. Everybody, meet your new best friend, the question mark operator. It's basically a magic spell for error handling. This one single character does the exact same thing as that entire match block we just saw. If the operation works and returns okay, it just unwraps the value and moves on. But if it returns an error, it immediately stops and returns that error from the function. It is clean, it's concise, and it is just so powerful. Okay, as you continue on your coding adventure, you are absolutely going to run into some challenges. But don't think of them as errors. Think of them as compiler dragons. See, the compiler isn't trying to be mean. It's actually your helpful guide, pointing out all the dangerous traps before you fall into them. So let's talk about the dragons you'll probably encounter the most. First up, the classic. Trying to return a reference to some data that was created inside a function. The compiler is going to stop you right there, because that data is about to be destroyed. The other common ones are really just variations on that same theme, trying to use a piece of data after you've already given ownership of it to someone else.
And here is the golden rule for slaying that first dragon. Don't return a reference to local data. Just don't. Instead, return the owned value itself, like a string instead of an and star. This properly transfers ownership to the function that called it, which is exactly how the whole ownership system is designed to work.
So let's bring this all home. With these tools and these strategies in our back pocket, we can now really talk about the art of writing truly robust, reality-proofed Rust code. If you take away anything from this, make it this mantra right here. 1. Use result for things that can actually fail, and option for things that might just be missing. 2. Let that magical little dot operator do all the heavy lifting for you. 3. When in doubt, just transfer ownership by returning an owned value. And 4. Make your own custom error types. It makes your code's failure modes so much clearer. Following these principles makes your code incredibly robust. It can handle the messy, unpredictable real world without ever sacrificing that memory safety we love. But there's another dimension to all this: time. How do you prove to the compiler that your data is going to live long enough to be used safely? Well, that, my friends, brings us to our next topic: lifetimes. This explainer was brought to you by Forge College. If you're ready to continue your adventure into Rust, Solana, and the wider world of Web3, you should definitely visit them at forge.college. Thanks for hanging out with me on this one.